Hey everybody, in this video we want to wrap up equilibrium and talk about the solubility product and how that relates back to equilibrium conditions or equilibrium calculations. So I'm going to dispel a big lie. I know, it's what happens. You learn more and more and you realize that you actually learn less and less. Okay, so the big lie is that there are two types of solubility. Either things are soluble or they are insoluble. It turns out that everything can be, anything that is not soluble actually is soluble just to a very small degree. So solubility is not black or white, it's a sliding scale of solubility. Okay, so there is so if something is completely insoluble, that would be really strange. Compounds have some degree of solubility. So one of the compounds that we may look at is barium sulfate. Barium sulfate isn't, as we learned our solubility rules, we would say that barium sulfate is not necessarily soluble, okay? But what it does is it forms an equilibrium reaction where some of it will react and ionize. Now, this reaction is a solubility reaction because when something dissolves in water, it forms its ions, okay? Now, the equilibrium is going to lie really far over this way, but still, we have some of this in the solution. And a lot of times, it's just a mathematically insignificant number. But for some cases, it is significant because what if we have something like lead? And so in no cases are lead ions good to have in your body. What if we have lead in our drinking water? Okay, there was a case where in Flint, Michigan, there was lead in the drinking water, and you only need a little itty bitty tiny bit of lead in your drinking water for it to be dangerous. And so even though we say that lead compounds are typically not soluble, they are to a tiny degree, and we need to keep that in mind when we're what I would say doing chemistry. Okay, but now let's write an equilibrium expression for this. Now, this is a K, and K is going to be products over reactants. And now look at what this is. It's the barium, Ba2+, times SO4 2-. Okay. Now notice here that this is a solid, so this doesn't play a role in the equilibrium expression. Okay, and what kind of reaction is this? This is a solubility reaction. And what's the answer when you multiply two values together? It's a product. So this is a solubility product. That's where you get Ksp from. Okay, and so this is how we measure the solubilities of things that are very slightly soluble, or sometimes you'll see sparingly soluble, or even things that we consider insoluble. All of these things have, all of these compounds have some solubility in water. Okay, so there's the equilibrium constant expression, and that K is called the solubility product. So I think it's important for us to look to go through a problem. So let me call up a problem and we'll go at it here. So I called up some sample problems. So let's work through some of these because I think this will help us with the math of Ksp. So the molar solubility of lead bromide is this. Okay, this is a value. Find the Ksp. Now, Ksp is still an equilibrium problem, and the rules of Ksp, or the rules of equilibrium, still apply to Ksp. there are two types of equilibrium problems. Find the constant, find the conditions. Well, this is find the constant. So that means that somehow this number is going to be the conditions. Okay? It's going to give us the conditions. So let's write a balanced chemical equation. Okay, so we get PbBr2 solid is in equilibrium with Pb2 plus 2Br minus. Now, these two things are aqueous. And before we get too far into this, I want to point out that we have a coefficient here. So we have to remember that that coefficient plays a role in the equilibrium expression. So just be careful because we haven't used or seen coefficients in a while. Okay, so what does it mean that the molar solubility is this? Okay, well, that means how many moles dissolve. So what this is, in short, is our X value. This is how much. At the beginning, this is 0 and this is 0. And this tells us that for every 1 mole of this that dissolves, we make 1 mole of this. This tells us what our X value is. So we are going to gain plus 1.0 times 10 to the minus 2 molar, okay, lead. And so now here, keep in mind that we're getting 2 bromides. So this is double that, 2.0 times 10 to the minus 2. Okay. So now at equilibrium, there's 1.0 times 10 to the minus 2, and this is 2.0 times 10 to the minus 2. So what do? Okay, well, now we figure out Ksp. Okay, so this equals the concentration of Pb2 plus times the concentration of Br minus, and that is squared. Keep in mind that this 2 is for the stoichiometry, and this 2 is for the equilibrium. Two different applications, and so you have to do it both times. It's a big hang-up. So 1 times 10 to the negative 2 times 2.0 times 10 to the negative 2 squared. And so now we'll plug that into our calculator. So we have 1 times 10 to the minus 2 times 2 times 10 to the minus 2 squared. Now orders of operations, it's going to square the 2 times 10 to the minus 2 first. Okay, so that should be good. So we get an answer of 4 times 10 to the minus 6. So our Ksp is 4 times 10 to the minus 6. And that's a fairly big Ksp. It's still a small number, but for a Ksp, I would say that that's pretty big. Okay, so what are some other types of problems you could see? Okay, so here now it says find the solubility product constant. Again, that's a fancy way of saying Ksp. And so two types of problems. There is a find the expression, or sorry, find the constant, find the conditions. In this case, we have to find the constant. So this should tell us what the conditions are. Okay, so let's go. PbI2. And so in these sorts of reactions, okay, these sorts of Ksp reactions, they're always kind of the same. So lead iodide separates into lead 2 plus 2I minus. Both of these are aqueous. This is aqueous. This is solid. Okay, and so now we can determine how much of this we have. How do we determine that? Well, we can figure out if this is how many grams of lead iodide there is. We can convert this to moles and then divide by the volume. Okay, so we kind of have to do that in order to do the Ksp value in here. So lead iodide. Okay, so lead, there's how many leads in this? Pb equals 1 times 207. And then iodine, there's 2 times 127. Oops, 127. And so now we go 207 plus 2 times 127. Those masses are right off the periodic table. So the mass is 461 grams per mole. Okay. So now how many grams do we have? We have 0.054. So I'm sorry, 0.54, not 0.054. So now if we're going to do this, we're going to go 0.54 times, grams, and I always use X line, okay, grams on the bottom, moles on top, and it's 461 grams for every 1 mole. And so we're going to go 0.54 divided by 461, and that's going to give us 1.17 times 10 to the minus 3 moles. Now, to get the concentration, we divide by the liters. So this is divide by liters, and it's 1 liter, so it stays that molarity. Now, that tells us how much of this dissolves. Well, if that's how much dissolves, for every one of these that dissolves, one of these is being made. So this is another way of giving us our molar solubility. So this is 1.17 times 10 to the minus 3. Okay, and then this is 2 times that, so it's 2.34 times 10 to the minus 3. Okay, 0, 0, plus, plus. All right, we're doing our IC chart. I'm progressively getting worse at writing my IC charts. Okay, and so in the end, IC, remember this doesn't matter because it's a solid, so this is 1.17 times 10 to the minus 3, and this is 2.34 times 10 to the minus 3. I don't know why I doubled it. So, okay, so now we calculate our KSP. KSP equals 1. Let me not jump ahead here because you haven't seen this enough. So this is the concentration of Pb2 plus times the concentration of I minus squared, right? This is the equilibrium part. We have to keep the equilibrium part separate from the stoichiometry part. So we go 1.17 times 10 to the minus 3 times 2.34 times 10 to the minus 3 squared, and now we math it. Okay, so 1.17 times 10 to the minus 3 times 2.34 times 10 to the minus 3 squared. Again, orders of operations. The squared is going to happen before the multiplication. So we get that KSP equals 6.41 times 10 to the minus 9. Okay, and that's our KSP. So this is the last type of equilibrium problem we're going to get into, where we're going to try to predict whether a precipitate is going to form. Okay, so when we mix PbNO3, lead nitrate, with sodium sulfate, Na2SO4, both of these are soluble, and when we mix this in the lab, we would actually see a reaction where we're going to form an actual solid. Okay, and that solid is going to be lead sulfate, and then there actually is another product, and that's sodium nitrate. But the idea is now that these concentrations are so small, and we know that that solids actually can dissolve a little bit, even though that they're not fully soluble. You know, we want to know what's the kind of the how much is actually going to dissolve. Will a precipitate form? Okay, so now this type of question leads us into that sort of Flint, Michigan story where, you know, how much lead is too much lead, or how much lead are we going to have in in the water. Okay, so this is a double replacement reaction. This is the product of the double replacement reaction. So what we want to do is we want to take this and we want to know how much lead sulfate there will be once we do the reaction. Okay. Now, this in its simplest form is just a Q versus K problem. Okay? That's really what it is. So what we want to do is we want to calculate how much sulfate there is at equilibrium, or at initially, and how much lead there is initially, and then we're going to go from there. The problem with that is that we have to do some math to get at that point. Because, let's see, because we're mixing 100 milliliters of this and 400 milliliters of that, so that you end up diluting them and you end up having to calculate a new concentration here. Because if we're going to do the math, remember this is still kind of an equilibrium problem, and that needs to be done in molarity. Okay? So, where do we go from here? Well, if we want to recalculate these things, we have to do the math for lead. Well, how much do we have initially? Okay, well we have 0.1 liters of 8 times 10 to the minus 3 lead nitrate. Okay, so we have 0.1 liters.
Pardon this interruption.
Sorry. Okay, 0.1 liters, and so we X-line it. Okay. Oh, I'm sorry, I'm doing the wrong thing here. Okay. We're doing a, it's because I had an interruption. Okay. Because it's diluted, we have to use M1V1 equals M2V2 to calculate what the new concentration of lead ions is in the new solution. Think about it. If we mix the lead nitrate into 400 milliliters of solution, it's going to be even more dilute than just the 0.1 molar. So this is the formula that we use. Molarity times the volume, kind of at the beginning, initially, is equal to the new molarity times the final volume. Well, what is the old molarity? The old molarity is 8.0 times 10 to the minus 3, and the old volume is 0.1, and that equals whatever the new diluted molarity is going to be times the volume. And the new volume is 0.1 liter plus 0.4 liters, which equals 0.5. So now we do 8 times 10 to the minus 3 times 0.1 divided by 0.5. And so what we have is a new concentration of lead. So that new concentration of lead is 1.6 times 10 to the minus 3 molar equals the concentration of lead 2 plus. Okay. Now we do the same thing with sulfate, SO4 minus. And so here we go up and we see, okay, so it's 5 times 10 to the minus 3, and we have 400 milliliters of it. So M1V1 equals M2V2. Okay, and so what is the old molarity? 5.0 times 10 to the minus 3. And how much of that did we add in order to the mixture? 0.4. And that equals your new molarity, M2, and then times the new volume, 0.5. So 5 times 10 to the minus 3 times 0.4 divided by 0.5, right? And so that's going to equal 4 times 10 to the minus 3 molar is equal to the concentration of SO42 minus. Okay. Sounds awesome, right? So now we want to compare Q to K. Well, the concentration that we're worried about here is 1.6 times 10 to the minus 3. And the concentration of sulfate is 4.0 times 10 to the minus 3. 4.0 times 10 to the minus 3. Okay? And so now if we're going to calculate Q and compare it to K, what that's going to tell us is which way the reaction is going to shift. Is it going to shift this way towards the reactants, or is it going to shift this way toward the products? And that's going to be the question. And so what I like about doing this kind of at the very end of the equilibrium unit is kind of circles all the way back around to almost the very beginning, where we have to know Q and K. Okay? If it shifts left, what do we know? This thing is a solid. It will precipitate. If it shifts right, well, these are ions. It's going to not precipitate because the ions have yet to be saturated in solution. So in order to do this problem, let's calculate Q. Okay, so Q equals concentration of lead times the concentration of sulfate. And so that's going to be 1.6 times 10 to the minus 3 times sulfate, 4 times 10 to the minus 3. And we multiply those together. So 4 times 10 to the minus 3 times 1.6 times 10 to the minus 3. And we get 6.4 times 10 to the minus 6. Okay? Now, we compare that to Ksp. Okay? So Q in this case is greater than K. Okay? Now, I never memorize those rules. Like if Q is greater than K, it shifts this way. If K is greater than Q, whatever. What I know is the chemistry behind it. And the chemistry is that K and Q are trying to become equal. It's trying to reach equilibrium. So in order to do that, if Q is greater than K, Q has to get smaller. So in order for Q to get smaller, let's look products over reactants. That means the products have to decrease and the reactants have to increase. So when Q is greater than K, in this case, the reaction is going to, let's say the products have to get smaller, reactants have to get bigger, so the reaction is going to shift in this direction. So if it shifts in this direction, it's going to form a precipitate. So this reaction will precipitate. Okay? So that's Ksp. I hope you have some idea of how non-soluble or insoluble salts behave and how we can predict precipitation. Have a great day.